Hello everyone. Today we are going to discuss about coherence. Two wave sources are perfectly coherent if they have a constant phase difference and the same frequency. Coherence is an ideal property of wave that enables interference. Coherent sources are those which emit light wave of same wavelength or frequency and have constant phase difference. Example of coherent light is laser light, and in case of incoherent light it is laser light. Now what is the main difference between ordinary light and laser light? In case of ordinary light it emits many wavelength, it is multidirectional, that's why it is incoherent. In case of laser light it is monochromatic, it emits in one direction and it is coherent source. Another necessary condition for wave to be coherent is that both wave travel at same speed. It is measure of the correlation that exists between the phase of the wave measure at different point. It is the coordinated motion of several wave maintaining a fixed and predictable phase difference. Consider two waves perfectly correlated for all time. If combined, they will exhibit complete constructive interference at all time. It follows that they are perfectly coherent. If we want to draw the diagram of coherent and incoherent light, we can draw as shown in figure 1 and figure 2. Now what is temporal coherency? It is the correlation between the phase of a wave totally different point on the direction of propagation. It is correlation between the wave at one point at different time along the path of beam is called temporal coherency. It is related to the emitted line width. Let us consider a single point on the wavefront. There will be a phase difference between time t is equal to 0 and t is equal to 6t of the wave. If the phase difference remain same for any value st, then the wave has perfect temporal coherency. But if this is only for specific value of s6t, then the wave has partial temporal coherence. What is spatial coherence? In case the phase difference remains same for any 2 point anywhere on the wavefront, then the wave has perfect spatial coherence. Whereas if this is true only for a specific area, then the wave is said to have only partial spatial coherence. It is correlation between the phase of light wave at totally different point transversal to the direction of propagation. It is correlation between different places but not along the path. It is expounded to directionality and uniphase wavefronts. Now let's discuss about the difference between temporal coherence and spatial coherence. Temporal coherence is concerned with the phase correlation of wave at a given point in the space at two different instants of time. Spatial coherence is concerned with the phase correlation of two different points across a wave front at a given instant of time. Temporal coherence, the type of coherence related with time. In spatial coherence, it is related with position. In temporal coherence, it is known as longitudinal coherence, and in case of spatial coherence, it is known as transverse coherence. The temporal coherence of light is related to frequency bandwidth of the source, that is monochromaticity. Spatial coherence is related to size of light source. Temporal coherence measure in interferometers such as Michelson interferometer. Spatial coherence measure in interferometer such as Young double slit interferometer. Now let's discuss about coherence time, coherence length, spectral purity factor. The average time interval for which definite phase relationship exists is known as coherence time. The distance capital L for which the wave field remains sinusoidal is given by coherence length capital L. It can be written as capital L is equal to C into tau. Coherence length can also be written in terms of frequency. As we know that tau can be written as del t, which can also be written as 1 upon del nu. Also, we know that nu is equal to C upon lambda. Differentiating equation number 3, we get equation number 4. We also know that spectral purity factor is given by Q is equal to lambda upon del lambda. Therefore, L can be written in terms of spectral purity factor as L is equal to lambda Q, equation number 7. Here, coherence time tau can also be written in terms of spectral purity factor as tau is equal to lambda Q upon C as given in equation number 8. Now let's discuss about interference visibility. A quantity measured of the coherence of light source is equal to the visibility capital V of the fringe. The fringe visibility is defined as capital V is equal to Imax minus I minimum upon Imax plus I minimum. The value capital V ranging between 0 to 1, if V is equal to 1, implies very high contrast fringes. The fringes are washed away when V is equal to 0. The value greater than 0.88 indicate that light is highly coherent. Now let's talk about interference visibility as a measure of coherency. Let us consider two interfering waves, each of intensity I. Both the wave consist of coherent part IC and incoherent part INC. If C degree of coherency, then IC can be written as C I naught. INC can be written as 1 minus C I naught. Equation number 1 and equation number 2. When superimpose, the coherent part shall interfere adding their amplitudes, whereas for the incoherent part the intensities are simply added. Therefore, Imax is equal to 4 IC plus twice INC, and I minimum can be written as 0 plus twice INC, equation number 3 and equation number 4. Putting the value of equation number 1 and 2 to equation number 3 and 4, we get I max and I minimum equation in equation number 5 and equation number 6. As we know that interference visibility given as V is equal to I maximum minus I minimum upon I maximum plus I minimum. Putting the value of I maximum and I minimum and solving this equation, we get capital V is equal to C. Therefore, it is seen that degree of contrast is a measure of degree of coherence between wave of equal intensities. In this way, we have completed the topic coherence. Thank you.